This video is going to be the last video of this chapter and will be used to go through 3 different example problems relative to the content of chapter 2. So let's go ahead and start with the first problem. The first problem reads, a water pump that consumes 2 kilowatts of electric power when operating is claimed to take in water from a lake and pump it to a pool whose free surface is 30 meters above the free surface of a lake. And it claims that it pushes the water, or the flow rate of the water is 50 liters per second. You are to determine if this claim is reasonable. So this problem is saying, I have a pump that's consuming 2 kilowatts of power and it's able to move water 30 meters high at 50 liters per second. Is this true or not? Right, and you need to determine that. So let's go ahead and start with the schematic. Here's my schematic. Let's go ahead and correct that typo, please. All right. So here's my schematic. I have here my a little bit. I have a lake on the bottom. I have a reservoir on the top, and I have a pump moving water to the top of this reservoir, where the top of the reservoir is 30 meters above the lake on the bottom. So before I even get started with anything, I'm going to draw a few assumptions here. My first assumption is going to be that this pump is operating at steady state, right? That means that it's at a constant flow and the state of the system is not changing. Number 2, I'm going to assume that the fluid flow through the pipes is frictionless. And number 3, I'm going to assume that there's no change in kinetic energy. All right, so let's think about what's going on here. The problem statement is claiming that I can move water at 50 liters per second. I can move it 30 meters high and only consume 2 kilowatts of power. Is that reasonable or not? So in order for you to prove whether it's reasonable, we need to look at what is the minimum power necessary to do that, right? And the minimum power necessary is, can we increase potential energy of this water? Can we increase this potential energy to pull it up? Is 2 kilowatts enough to increase its potential energy to move the water at 50 liters per second, 30 meters high? Right, that's basically what it's saying. So if we can prove that it takes less than 2 kilowatts of energy to move 50 liters per second of water 30 meters high, just by increasing its potential energy, then we can show that this claim is reasonable. But if not, it's unreasonable. So how do we do that? Well, in our analysis, we're going to have to show this through a first law analysis, right? First law analysis, we're going to write it out in rate form because this is a rate problem since the water is flowing. En, the rate of energy into the system, minus the rate of energy out of the system equals the rate change of energy of the system. So in order to do a first law, we need to first go back to our schematic and to draw what our boundary is. And for me, I'm going to use the boundary to be the entirety of the pipes and the pump. All right, so with that said, we're going to go ahead and substitute in what energy transfers by heat, mass, and work are going in, minus whatever energy transfer turns by heat, mass, and work out, equals the change in energy of the system. But before we do this, right away, we're going to look at this first law in compact form. There's already one term that's going to go away, right? If we think about it, the system is at steady state. That means the state of the system is not changing. If the state of the system is not changing, the change in the energy of the system is 0 because the state's not changing, therefore the energy is not changing. So since the system's at steady state, my change in energy of the system is 0. Think about it. If I have 5 kilojoules of energy at state 1 and state 2 also has 5 kilojoules of energy, the change in energy of the system is 0. So the system is at steady state, meaning that the change in energy of the system is 0. So here, this gets reduced down to En equals E out. Great. So I just made my first step. Now, with that, now I need to go ahead and I got to say, okay, what are my En terms and what are my E out terms, right? Now, we talked earlier that energy is transferred in 3 forms, only and always either by heat, mass, and work. Heat, mass, and work. Energy is transferred by heat, mass, and work only. So let's look for those 3 mechanisms. This pump doesn't really have any heat transfer to it, right? So we can actually add that as another system. We can assume there's no heat transfer, right? So there's no energy transfer by heat. There's energy transfer by work into the system, right? There has to be work in because the pump consumes energy in order to move the water. Therefore, there's work into the pump. There's water entering into the system since it's being moved up. So that means there's energy by mass of the water into the system. And then the water's exiting the system, so the energy by mass out of the system. There's no heat out because we just showed that there's no heat transfer going on. And there's no work coming out of the system, so the only energy coming out has to be by mass. So if I go ahead and substitute these back into my first law, I get work in, remembering that work in is negative based on our sign convention that we talked about earlier, plus energy by mass in, equals energy by mass out. Great. That's the first step. Now, what is the energy by mass in and what is the energy by mass out? Well, in this case, we're looking at the minimum energy necessary to move the water, which we just in terms of increasing the potential energy of the water. Do I know what Z1 is? Do I know what Z1 is? Do I know what this height is right here? No, I don't. But I know that to change in height, if I go ahead and pull my potential energy terms to one side, I know that my delta Z is 30 meters, right? So I can just go ahead and substitute in my terms. So what is mass? Well, I don't know what the mass flow rate is. This is mass flow rate. I don't know what it is, but I know my volume flow rate, 50 liters per second. I can multiply that by the mass of water. I know it to be 1 kilogram per liter. Multiplied by gravity, 9.81 meters per second squared, multiplied by the change in height, which is 30 meters. So those are my terms that I know. But I'm not done yet because when I go ahead and do this, you're going to find that I have this narrowed down to be kilograms per second times meters squared per second squared, right? And so I have to actually convert. If you go back to your book, you'll find that 1,000 meters squared per second squared is equal to 1 kilojoule per kilogram. So I have to include that term in here in order to convert my meters squared per second squared, which is usually what happens when I'm dealing with potential or kinetic energy terms, to convert it from meters squared per second squared to kilograms to kilojoules per kilogram. So when I finish this off, I get that my final amount of energy is 14,750 joules per second, which is equal to 14.75 kilowatts, right? So since I found out that the energy required for the pump to move the water at 50 liters per second to move it 30 meters high, I need at least 14.75 kilowatts just to move the water. And 14.75 kilowatts is, of course, greater than 2 kilowatts. Therefore, according to that, the claim that it only consumes 2 kilowatts is false. Excuse me, let me rewrite that. The claim is false, right? So we just proved that the claim is false based on a first law analysis. All right, so that's the first example problem. We're going to go ahead and move forward to completing 2 more. So with that said, let's go ahead and look at the second one. Here is the second one. It's very similar to the last one. Water is pumped from a lake to a storage tank 20 meters above at a rate of 70 liters per second while consuming 20.4 kilowatts of electric power. Disregarding any frictional losses in the pipes and any changes in kinetic energy, determine A, the overall efficiency of the pump motor unit, and B, the pressure difference between the inlet and the exit of the pump. So first thing is a schematic, which is already done for you. Here's a schematic of the pump moving water 20 meters high to a storage tank. Next step is to make assumptions, right? First assumption based on what the problem statement gave us is assuming that the change in kinetic energy is 0. Number 2, we're going to assume this to have frictionless flow through the pipes. Number 3, like in the previous problem, we're going to look at this as a steady flow problem. And then number 4, we'll go a step further and assume that the lower water level is at a height, let's say at a height of 0. That was supposed to be an at, like an at in an email. All right, so let's go ahead, and part A is asking for the overall efficiency of the pump unit. So this problem is stating that the motor consumes 20.4 kilowatts, right? So an efficiency would be what is the minimum amount of energy necessary for it to move the water versus how much energy it actually takes to move the water, right? Let's go ahead and do a first law analysis much similar to the prior problem. E in minus E out equals delta E system, right? Since the problem is at steady flow, delta E system is 0, resulting in E in equaling E out. Much like the prior problem, if I take my system to be the pipe and the pump, I have energy in by work and potential energy of the fluid, and I have energy out by potential energy of the fluid. So I have work in, by bringing in the mass term on the other side, is equal to mg delta z. So what is my mass flow rate? I can figure out my mass flow rate based on, excuse me, let me go ahead and erase that and write that out again. My mass flow rate is going to be m dot equaling the density times the volume flow rate. The density of water is 1 kilogram per liter, and the flow rate of the water is 70 liters per second. So my mass flow rate is going to be 70 kilograms per second. So if I were to finish out my work term on the next slide, I would get that work in is equal to the mass flow rate times gravity times the height multiplied by the conversion that we looked at earlier, where we have to convert when we're dealing with kinetic energy or potential energy term, which we have in this case, is 1 kilojoule per kilogram is equal to 1,000 meters squared per second squared. That gives me a work in of 13.7 kilowatts. So it's asking for the efficiency. So the efficiency would be the minimum amount of energy necessary just to move the water, which is 30.7 kilowatts, divided by the actual amount of electrical energy that the pump is consuming, which is 20.4. So that tells me that this pump is operating at 67% efficiency because it's consuming more energy than is minimally needed. So that extra energy that is consuming, right, the extra energy above 13.7 kilowatts is due to inefficiencies in the pump, right? And then part B, if you go back to the problem statement and recall what part B is asking, it's asking for the pressure difference between the inlet and the exit of the pump. So what's the pressure difference going to be? Right? We think like, oh, wow, how do I get the pressure at the outlet of the pump? It's asking for the pressure difference. And what is basically the pump doing? The pump is moving water 20 feet high. So therefore the pressure would be the water at 20 feet, right? Remember we talked about pressure is just basically depth, right? So if really what the pressure difference between here and here is just the height of the water. So if you go back, this is actually a problem like from chapter 1 The height of the water, well, it would just be the density of water times the gravity times the height that the water was moved. So if you actually do the math and write it in, this is going to be 20 meters. This is going to be 9.81 meters per second squared. The density of water is 1 kilogram per liter. If you do all the math and the conversions, which I'm not going to do, you would find that the total pressure is 196 kilopascals. That's going to be the pressure difference across the pump. As we further on, as I just started here, I'm going to do less and less of writing in all of the units and all the necessary unit conversions in order to get the answer to the specific units that are asked. I am not going to be going through all of that in the example problems because I believe that's something that you guys can do once you practice on the homework. So what I'll end up doing a lot now with example problems is just writing out the final solution in terms of the equation, and then depending on you to be able to know how to fill in those terms and to be able to do the proper unit conversions to get to the final answer. Okay, so with that said, that's our second problem. We have one more problem